anything written at all, you need to remember that's assumed to be 10. So looking at a couple of these, we can evaluate these things either by using a calculator or by using some basic exponents. So like, for example, if we were going to try and evaluate the common log of 1,000, we're trying to figure out what value that is. Again, this is just a different way to rewrite an exponent. This is saying 10 to what power equals 1,000. And if you rewrite 1,000 as 10 to the third power, it becomes pretty apparent, well, if 10 to the third is equal to 10 to the x, well, then that means that x right here should equal 3. And if you double check that using a calculator, so let me pull out a calculator here real quick, and you do the log of 1,000, you can see that evaluates to be 3. So then let's look at another one real quick. So if we do the log of 0.01 and this equals x, if we say 10 to what power is going to give me 0.01, this might help if you see the math fact here that 10 to the negative second power is 0.01. So we can rewrite this as 10 to the x power equals 10 to the negative 2. So that clearly means right there that x is going to have to be equal to negative 2. And so in general, to generalize this, if you see the common log of 10 to the x power, whatever that power for x is, that's going to be the solution. So like if you saw log of 10 to the fourth power, it's saying what power do you have to put 10 to get 10 to the fourth? Well, it's the fourth power. And it may seem like some common sense, but it's just breaking down the basics of logarithms there. So let's look at this a little bit in practice. So if we look at the log of 100 here, this is saying 10 to what power equals 100. You can probably get that without having to rewrite 100 as a base of 10, but Mr. Price is going to rewrite it anyways. 100 is 10 to the second power, so that means if you evaluate this, you can get 10 to the second power will equal 100. And then the same thing over here, this is asking 10 to what power is going to equal 0.1. And if we use the fact here that 10 to the negative first gives us 0.1, 1/10, then we'll say 10 to the x equals 10 to the negative 1. So that means that x is going to be negative 1. And we can easily use a calculator to evaluate those to confirm what we were finding. Log of 100, log of 0.1. And you can see those. I just want to give you all an intuition for how those are calculated. So in general, for logarithms that are not perfect powers of 10, we want to use a calculator to evaluate these. So like 10 to what power gives me 8? I'm not exactly sure there. It's going to be a number less than 1 for sure, but that is about all that we can say. So let's see. So we'll say 10, oh, excuse me. So we're going to write the log of 8 equals x there. So then log of 8 is x. So then we'd say 10 to the 0.903 equals 8. So I want you all to go ahead and do that for these other two real quick. Take a second, pause the video, and do this on your own. Mr. Price is going to go ahead and chug along and do these. Log of 800 equals x. Common log of 0.08 equals x. And let's see here. So log of 800. So that means that 10 to the 2.903, or I guess I should have said 2.90, excuse me. We're rounding to 2 sig figs there, equals 800. And then over here for the log of 0.08, 10 to the negative 1.1 is going to equal, not x, excuse me, 0.08. And remember, the whole purpose of these logarithms is we're trying to find what exponent can we put something to and have it evaluate well. So let's look at two more real quick. Using a calculator. So we're going to look at the log of 2. So using our calculator to evaluate this, so the log of 2 is approximately 0.301. And if we look at the log of 20 here, you can see that is 1.301. And so the second question here for this example is saying, okay, explain why the log of 20 is the log of 2 plus 1. We want to explain why the log of 20 is the log of 2 plus 1. So think about that for a second. Can you figure out a reason why? And so it kind of has to do with what 1 is the equivalent of. So I want you to think about what logarithm could you write this 1 as? So like if we're using a base of 10 here, what would Mr. Price have to put inside of this log? So 10 to what power is going to give me an answer, or excuse me. So if I want my logarithm to end up with an answer of 1, so I want this x to be 1. What has to be in there for that answer? And the answer to that is 10. So I can replace this 1 right here. So log 2 with the log of 10, because the log of 10 is the same as the log of 1. And so with that, we have a property. We're not going to go on this super long. There is a property that says that if you've got the log of A times B, that you can break this up into log of A plus the log of B. And the reason that you can do that, logarithms are directly related to exponents. So like if you think about how you have x squared times x cubed, well, the way that you simplify this is you go and you rewrite this multiplication right here as x times 2, or x to 2 plus 3, which gives us x to the 5th. Logarithms kind of work the same way, where we've got a times b. We can rewrite that as separate logarithm addition. So the log of 2 plus the log of 10 is the same thing as the log of 2 times 10. We're condensing that thing. And we won't see a ton of this today, but it's just something I want to make you all aware of. We're not going to work an incredible amount with those properties. So the common log will pop up a ton, just because the number 10 pops up a lot in mathematics. And so let's look at a quick example of where you can see a logarithmic model used, and then we will move on to the natural log. So the magnitude, so this is on page 207. So the magnitude of an earthquake, which releases E joules of energy, is given by the magnitude is equal to 2/3 times the log of E divided by 10 to the 4.8. And so what we want to do is we want to find the magnitude. So we want to find M for an earthquake which releases 5.1 times 10 to the 10th joules of energy here. So let's see, we've got 2/3 times the log of 5.1 times 10 to the 10th over 10, 4.8. We want to know what kind of magnitude is this going to cause. So Mr. Price does not exactly know what that's going to be off the top of his head. So what he's going to do, let's see, I believe it's alpha y equals to get a fraction. Yeah, that's going to make my life a lot easier. So we're going to do 2/3 of the log. I'm going to use alpha y equals again, get another fraction. That makes my life just a lot easier than having to use all those parentheses. And if you didn't know that, well, you are welcome, because that is a lifesaver. Alpha y equals just pulls up a fraction. So the magnitude of this is going to be a 3 point, we'll call that 9.4 magnitude. I'm sure that they would round that up to a 4. I'm not exactly sure how the magnitudes work, though. I need to get a refresher on that. So we'd say this is a 3.94 magnitude earthquake. 3.94. So decently sized earthquake. And so then the next thing that we're going to say is, okay, how much energy, so we're going to flip this thing. How much energy is released by a 4.3 magnitude earthquake? By a 4.3 magnitude earthquake. So let's see here. We've got a 4.3 equals 2/3 times the log 5.1 times 10 to the 10th over 10 times 4.8. And so what we can do, there's a couple approaches we can do here. So we can graph this thing. We can try to use a little bit of algebra and rewriting it. And you know what? I think we can do a little bit of both. So before we can write this thing as a logarithm, rewrite this as a logarithm, what we need to do is we've got to get rid of this 2/3 first. So to get rid of 2/3, it's multiplying. We're going to divide by 2/3. And when you're dividing something by 2/3, that's the same as multiplying by its reciprocal. If you're dividing by a fraction, so what we're going to have to do is we're going to multiply both sides here times 3/2. So times 3/2 over here, times 3/2 over here. And so these are going to cancel out. And what's going to come down is my log of 5.1 times 10 to the 10th over 10 to the 4.8. And you know what, Mr. Price, what are you doing, dude? We're trying to solve for energy here. We don't know what that is yet. That needs to be a big fat E there. I apologize, you all. I'm just a little bit rusty. So let's see. 1.5 times 4.3. So that's going to give us 6.45 on the left-hand side. And what we're going to do now is we're going to use the definition of a logarithm to figure out the magnitude here. So the base here, if it's not written, is 10. So we're saying 10 to this exponent right here, 6.45 to the 6.45 equals E divided by 10 to the 4.8. And so what we're going to have to do is we're going to have to multiply to solve for E. We're going to multiply both sides by 10 to the 4.8. So times 10 to the 4.8. And the, let's see here. What we can do, cross those out. We can either use a calculator, or we could just add those exponents. Either works. So 10 to the 4.8 times 10, oh goodness, 10 to the 4.8 times 10 to the 6.45. Okay, so our answer here, we're going to round out the 3 sig figs right there, is going to be 1.78 times 10 to the 11th power. Some good old, we're doing some science. It seems fitting that we use some scientific notation. So that is how many joules of energy that were expended for that particular earthquake. So if you wanted to do that a different way, you could go back to the original problem. If you want to graph 4.3 and you want to graph this graph right here, you could look for that intersection as well. It would be pretty high up because it's like 1,700 million joules, or maybe it's 17 billion. It would be a lot of joules is the point. And so finding the intersection there may be more difficult is what Mr. Price is trying to get at. So that is the common logarithm. So then let's talk about the natural logarithm a little bit. So the natural logarithm, if you're trying to find it on your phone, is ln right there. If you're using your calculator. Now you're probably looking at this and you're saying, Mr. Price, why on earth is it ln if it's natural logarithm? And the answer for that is that the people who discovered the natural logarithm spoke Latin, and so they gave it the name of Logarithmus naturalis, so ln. So whenever you hear me say ln or natural log, that's what I'm talking about. Or if I start speaking Latin, Logarithmus naturalis. And so you should, if you're watching these notes, you should have already done that bell ringer and discovered that constant right there, e. So e is a number so similar to pi that pops up in nature a lot. And so e is 2.71828, 1828, 4590, 45, 23. And I had a teacher who made me memorize it out to like 18 decimal places. It's actually not that difficult, but it's a number that's going to pop up a lot. And so whenever you see, whenever you're using a log with a base of e, we use the Logarithmus naturalis, the natural logarithm. And so instead of seeing it written log or log base e, you're going to see it written a lot with ln, the Logarithmus naturalis. And the properties for the Logarithmus naturalis are roughly the same as the common logarithms. They have the same properties. It's just the base that is different. And so, for example, if we want to try to figure out e to what power gives me e to the third, if it helps you when you're trying to evaluate these to rewrite this as log e to the third equals x, and then rewriting this. So we're saying this base right here to this exponent, and let me just write this, to this exponent right here is this answer. So e to the x equals e to the third. And so that just means that x right there is going to be 3. Also, typically try to stay away from corny math stuff, but this one is always too good to pass up. Really easy way to remember the order for what's what in a logarithm is if you remember that logs are bay, it goes base, answer, exponent. Logs are bay. You'll never forget it, I promise. That's every year. That's Mr. Price's favorite thing to teach is that logs are bay. It's why I became a math teacher. So then let's continue to look at a few more of these. So if we were doing ln of 1 over e to the fourth, we can rewrite that as the log of e, if that helps you remember, that's the base there. And then the inside here, if this is e to the fourth, this is the equivalent of e to the negative fourth. So we're asking ourselves, e is the base to what power here is going to give us this answer. So logs are bay here. So we're going to say, well, e to the x is equal to e to the negative fourth. So that means it is negative 4. So the last thing that we're going to look at here is we're going to use our calculators to write the following in the form of e to the k, where k is correct to 4 decimal places here. So the general rules for solving these work the same way when you're using a regular log. So here we don't know the exponent, so we're going to say log base e of 50 equals x, and that's really just ln of 50 equals x. So if you do ln of 50 right there, and we're rounding this to 4 decimal places, so we get 3.912, and you're wanting to check that. So we're saying that e to the 3.912 equals 50. If you're wanting to check that, if you look at that ln right there, their e to the x right there is the second option. So if you go to second and ln, it will pull up e, and then you can just punch in your power right there, 49.9988. We are rounding, so it's not going to be perfect. And then we're going to do the same thing for this problem right here. We're going to say, all right, the ln, we're just going to skip the log part, of 0.005 is going to be equal to our exponent there, ln of 0.005, and we get a value of negative 5.298. And again, you can always check whether you've done a log correctly, because it should, in theory, make your equation correct. So if you all have any questions on logarithms, please let me know. Shoot me a message or talk to me on Zoom. That is an overview of logs. That is as far as we are going to go in this class with them. So looking ahead next week, we will start reviewing for our exam on Monday, and we will have our next exam on Thursday. So I hope you all have a good weekend and enjoy your time off. Bye.